Section 12.3, Blackbody Radiation. You are looking at a black body. A beam of light can get into this cavity through this very small hole, and then it bounces around and gradually absorbed by the surface of the cavity. It can never escape out of this cavity because this hole is really small. So we can intentionally shed a light into the cavity, but the light can never get out. And then if we heat up this cavity, the atoms on the inside surface will move faster. They will eventually emit photons. If we wait long enough at a given temperature, let's say 6,000 Kelvin, the thermal energy of the atoms on the surface and the photon energy inside the cavity will eventually reach a thermal equilibrium at that temperature. The energy distribution will be the so-called Boltzmann Distribution. The probability of a photon or atom having a certain energy epsilon will be proportional to an exponential function, e to the power of negative epsilon divided by kBt. Kb is the Boltzmann constant, T is the temperature. Alright, again, imagine we heat it up to 6,000 K. The surface atoms emit photon into the cavity, and we have many photons inside, and they have a energy distribution. The photons have different energies. Well, this electromagnetic theory predicts that the spectral density of those photons is this. So what is spectral density? Well, you simply define a unit volume inside the cavity and measure its total energy. And then energy divided by the volume, you get this part, energy per volume. What does this mean? Per frequency range. Inside the volume, you have many photons with different frequencies, right? And then you can arbitrarily define a range. Let's say from 10 to the power of 14 hertz to 1.1 times 10 to the power of 14 hertz. You have a range. The range is 0.1 times 10 to the power of 14 hertz. Within that frequency range, you have a bunch of photons. Their total energy divided by the volume, you get the spectral density, which is again the energy per volume per frequency range. Okay, we're not going to prove this. This is from the electromagnetic theory. It's accurate. It's correct. The problem in analyzing the experimental value of this rho, the spectral density, resides in the calculation of this so-called average oscillation energy. So this bar is average. We're talking about the oscillation energy here of the atoms on the surface. The classical mechanics predicts the oscillation energy of the surface atoms is simply kBt. T is the temperature, K sub B is the Boltzmann constant, K sub B is R over the Avogadro constant. R is the ideal gas. So now we have this equation over here based on the classical mechanics prediction over here. So we need to use the prediction from the electromagnetic theory. This is correct. Okay, this one from oscillation energy to kBt, that's from the classical mechanic prediction of thermal energy. Now if we look at this equation, we can see rho is proportional to nu squared. Nu is the frequency. Alright, so how does this prediction match with the experimental result? Let's look at the 6,000 K data. And this yellow dashed line is our prediction. Rho is proportional to nu squared. Nu is the frequency of the photon. So this is a quadratic function at 6,000 K. Now we have experimental data at 6,000 K. It's this. What do you think? Well, they do match at the beginning when the frequency is low. So maybe from here to here. The theoretical prediction matches the experimental data very well. But then as the frequency goes up, well, you can see the deviation increases as well. And now in this region is the so-called ultraviolet light region. I'm sorry, this is a frequency, and this number 8 means 8 times 10 to the power of 14 hertz. At this point, you are looking at ultraviolet light, and this is visible range, and this is infrared. So in the infrared range, the classical physics prediction matches with the experimental data. But in the ultraviolet region, well, it's just completely disaster. All right, so actually we call this ultraviolet catastrophe. If you look at some other temperatures, we have similar behavior. At 5,000 K, the value of the spectral density rho goes up first and goes down, goes up and goes down. 3,000 goes up and goes down. It never behaves like a quadratic function. So the classical prediction is wrong. And what is wrong? So first, this is correct, and then this is wrong. This equation is wrong. The average oscillation energy is not kBT when the frequency is very high inside the ultraviolet region, for example. So now let's look at the issue. In classical physics, we assume energy is continuous. And Planck thought about this discrepancy and proposed that if the energy of the photons were quantized in this format, then we can make corrections to this prediction, this yellow dashed line, to make it match with the experimental data almost perfectly. So again, over here we are assuming the energy is quantized. In addition, Planck assumed the oscillation energy depend on a quantum number n. N has to be an integer, and the energy has to be an integer times h nu. And this n is 0, 1, 2. Anyway, it's an integer. H is the Planck constant. Nu is the frequency of the light. Well, in this case, since we have all different frequencies, we're going to say all these frequencies have a common factor. All right. Now, how do we get the average? Well, this is from the theory of probability. So if we have different energies, each energy has a associated probability. We just need to sum it up. Okay, this is the so-called probability weighted average. Let me give you one example. Let's say you bought a lottery ticket. Let's say 1% chance you can win $100, and 99% chance you will get nothing. So the weighted average is 99% chance times nothing plus 1% times $100. The weighted average is $1. So if you spend more than $1 on the lottery ticket, and if you keep doing that, you will lose eventually. Now let's assume the Boltzmann distribution. This is the so-called Boltzmann distribution. We will prove this in statistical thermodynamics by looking at the entropy. The Boltzmann distribution allow us to maximize the entropy of the system isolated from its surroundings. So anyway, we're going to use this equation without proving this first. Over here on top, that's the probability. You can see this nh nu is the energy of a photon or a bunch of photons. kBt are just the Boltzmann constant and temperature. And this is a single exponential function corresponding to this specific energy, n times h nu. Down there, we sum up all possible energies. So this I can be from 0 to infinity. And again, this I is the quantum number. IH nu is the energy of the photon. But now we're looking at the entire range. So this is the probability. And how do we get the weighted average? Well, it's very simple. It's going to be the energy times the probability. And then we're going to sum up all possible energies. So again, this is just energy times its probability. So again, this is the $100 times 1%, and plus $0 times 99%, and you're summing it up. The math is not too bad, and we'll go over these mathematics in statistical thermodynamics. So anyway, if you evaluate this, the result is exactly h nu divided by e to the power of positive h nu over kBt minus 1. So over here, it's positive. There's no n here, no I here. So anyway, this is a fairly simple expression for the oscillation energy. But remember, in classical physics, this average oscillation energy is kBt. It's not this. It's just kBt. All right. So in quantum theory, we have this spectral density is equal to, well, this expression. This expression has this nu to the power of 3 on top, e to the power of h nu over kBt minus 1 on the bottom. All right. But when frequency is really, really small, if h nu is much smaller than kBt, we can expand this exponential function if you have learned Maclaurin series or Taylor series in a math class. So e to the power of x is simply roughly 1 plus x. If you don't believe me, you just use your calculator to calculate e to the power of 0.01. It's roughly 1.01. Okay, with a very small percent error. So my point is, if h nu is much smaller than kBt, let's say it's roughly 0.01, and then the value of this exponential function is going to be 1.01, approximately. In general, e to the power of x is just 1 plus x, approximately. That's why we can use this approximation. When we use this approximation, we simplify the equation, and now you can see we have nu to the power of 3 on top, nu on the bottom. So we have nu squared here. Rho is proportional to nu squared. We just proved that classical physics is correct as long as the frequency is small. What if the frequency is very high? What if nu is approaching infinity? In that case, you have this nu 3 approach infinity. You have this exponential function approach infinity. However, this is exponential. So this term approaches infinity much faster than nu to the power of 3. And therefore, rho approaches 0 when frequency approaches 0. So that solves the problem here. As frequency goes to infinity, rho should approach 0. And indeed, rho is approaching 0 based on quantum mechanical prediction here. All right, so that's nice. In summary, the failure of classical physics in predicting the spectral density in the high frequency range, especially the ultraviolet range, is called ultraviolet catastrophe because, well, the theoretical prediction from classical physics deviates from the experimental data completely. We have to assume energy is quantized to make accurate predictions in the ultraviolet region. That's what Planck did.